let's begin our discussion of hydrostatics. Clearly, when we're looking at problems in fluid mechanics, we can make a big subdivision. There are problems that we call static problems and problems that are dynamic. Static problems are problems in which the fluid is not moving. That's what we're going to be dealing with over the next 3 lectures. Those are relatively simple problems. The more interesting problems are the problems when the fluid is moving, and that's what we refer to as fluid dynamics. But so let's go back here and start discussing hydrostatics. So as I said, it's very simple because the fluid is not moving. The fluid is at rest. So the typical scenario is one in which we have, for example, a fluid. Let's say this is the surface of the fluid, so where the liquid interfaces with, say, the air outside. So I typically draw a little triangle there to indicate where the free surface is. Most typically for us, it will be air on one side and, say, water on the other side. That's what that free surface separates for us. So if I have gravity, of course, which I would expect, obviously must be pointing in this direction, then I could have perhaps an object that is submerged in the water. And I am going to be interested when I'm looking at hydrostatics in determining what kind of forces are exerted on this object by the fact that it is submerged in water. Okay, now before we do that, there is a concept that you will have to become very familiar with. It's an abstract concept, but it's the concept of a fluid element. Clearly, fluid is an amount of matter, so it's made up of molecules, atoms, and so on. But in our view, in our so-called macroscopic view of the world, just like we did in Introduction to Thermodynamics, we're not really looking at the microscopic features, at the atomic or molecular features of the fluid. So we don't really need to think in terms of what those molecules are and what those molecules are doing, but we treat it as we look at the larger features. So the concept of a fluid element is very simple. Let's say that I have this fluid here. If I just make an imaginary volume within that fluid, so this dashed line represents a boundary in the way we studied in thermodynamics, a system boundary, so that whatever is inside here is a control mass. Or also, remember from thermodynamics, another word for that was a closed system. So this imaginary boundary encloses a portion of the fluid. There are millions of molecules in there, but that portion of fluid always has the same molecules in it. It's a control mass. That's the concept of a fluid element. And we use it a lot, particularly when we are deriving equations to see the laws, for example, Newton's second law, the first law of thermodynamics, the law of conservation of mass. We make use of this concept of a fluid element. So I'm going to take a fluid element, except my fluid element is going to have a very specific shape. So, and that specific shape will be like a wedge. So suppose I have a fluid element that looks like this. That's a fluid element inside my fluid. And let's say that this is in a condition of not motion. This is in statics. It's not moving. There is gravity. in the vertical direction. And let me put some coordinates here. Let's say that this is, I'm going to make this the z coordinate, and I'm going to make this the y coordinate. And the x coordinate is pointing out normal to the paper. So let me draw some forces that are acting on this fluid element. This fluid element is surrounded by fluid, and therefore, if I cut it out, I will treat it as a free body and do a free body diagram on it. So I'm going to put some forces on it. The fluid that is to the left will produce a force. The fluid that is to the bottom will produce another force here, and the fluid that is over here will produce another force. I'm not going to worry about the directions that are normal to the paper. So what are all of these? Let's give them names. Let's call this one F sub y, because it's in the y direction. Let's call that F sub z. And this generic one at an angle, we're going to call F sub s. So let's denote the angle here, call it theta, the angle of that wedge. And of course, that angle is also here. All right, so let's do a force balance. And let's do a force balance in the z direction. So if I do a force balance, I know from Newton's second law that the sum of forces must be equal to the mass of the fluid element times its acceleration. So let's do first the z direction. What do I have in the z direction? Well, we have this F sub z. That force, of course, will be equal to the pressure. Remember that the pressure is simply the force per unit area. It's a stress, pretty much like the shear stress was also a force per unit area, but the shear stress, remember, was a shearing force. This is a normal force. So the pressure is a stress in the normal direction. So if the pressure is the force per unit area, then of course the force is the pressure times the area. So this F sub z will be the pressure that is acting down here. Let's call that pressure P sub z times the area. And the area, of course, will be the area of the bottom of this wedge. And if I say that the vertical dimension of this is d sub z, and the horizontal dimension is d sub y, and then I have d sub x, I'm sorry, dx into the, this is not d sub y, dy and dz, and then dx into the board, then the pressure times the area is that. And then I have a component of this force that is acting also in the vertical direction. That's negative. Let's call this one simply P, or let's just call it P sub s on that angle surface. P sub s, and then the area is, let's say that this distance is ds, this hypotenuse of this triangle. So this is ds also times dx, right? Pressure times area gives me the force, so that's the F sub s. But now I need the vertical component, so I need to multiply this times the cosine of theta. And then, because I have decided that gravity is in the negative z direction, then I also have the weight of this fluid element, which is, let me draw it here, but pointing down, right? The weight of that element. And the weight of that element is the density times gravity times the volume of that wedge. So those are the forces, all the forces that are acting in the z direction, and therefore that must be equal to the mass times the acceleration in the z direction. So I will say that this is rho dv, which is the mass, times the acceleration in the z direction. So I have this expression. This is my force balance in the z direction. Now, what is the volume of this element? Well, it will be the area, which is the area of this triangle is dz times dy over 2 times the width into the paper, which is dx. So that's the volume of the fluid element. And another thing is that this there is a relationship, for example, between ds and dy. I can write that dy is ds times cosine of theta from the geometry of the drawing. All right. Okay, so if I use these last two relationships into my force balance, let's move that up there a little bit. Then, of course, I can simplify a lot of things. dx, for example, appears everywhere. So I can divide by dx. And let's see, the dy. So I have dy appears here. ds is dy over cosine theta. That will cancel the cosine theta. So this is what I'll have. pz dy will cancel, minus ps. I divided by dx. ds is dy over cosine theta, so that I'm also dividing by the dy, minus rho g. The dv is dz dy dx over 2. I divided by dx and divided by dy, but I still have the dz over 2. And then this is equal to rho dv az. Again, in the dv I divided by dx and divided by dy. So what I have here is rho az dz over 2. So that's the simplified expression for the vertical forces, for the balance of the vertical forces. But now we're going to do something very interesting. What happens if I now take this element and I let it shrink to a point? So let element shrink to a point. By taking simultaneously all of the sides to go to 0. Right? Make all the sides go to 0, shrink it to a point. This equation remains valid for any size, but as this element shrinks to a point, obviously the last two terms that involve dz will get smaller and smaller, and in the limit they will vanish. So as I take that limit, what I find is that pz minus ps, this becomes vanishingly small, so is that. So this approaches 0, which of course means that pz is equal to ps. And what is that telling me? That once I shrink this element to a point, let's draw the shrunk. So I went from a triangle to a point. Right? Once I have that point, if I draw my pressures again, so let's say that this is representative of the PS, and this is representative of the PZ, I find that they are the same. And since my angle was arbitrary, this could be any angle, theta, then really what I am saying is it doesn't matter what angle I chose for my wedge, for my element, I would always find that all of these values of the pressure that I would still call PS's would all be the same. And if you think about what happens then in the horizontal direction, if you do the force balance in the horizontal direction, the only thing that will be different is that in the horizontal direction there will be no weight, because the weight was all concentrated in the vertical direction. So if I do the force balance in the, say, the y direction, I wouldn't have this term involving the weight of the element. So I would end up with something that looks like this, but this would be P sub y, and this wouldn't be here at all. So the conclusion is, of course, that if I put the P sub y, which would be in this direction, then I have that the P sub y is also equal. So this drawing is a little bit too crowded there and small, but the conclusion is that the pressure is, of course, at a point is the same in any direction. Right? Pressure is the same along any direction. And therefore, that's what allows to conclude that the pressure is a scalar. Pressure is a scalar. We don't have to make a distinction about the pressure being different in different directions. It's the same in all directions. So that we arrive at by doing this force balance on this particular shape of a fluid element. All right, so let's take it one step further. Let's see. I don't think I need to do that yet. Let's do more or less a similar analysis, but this time we're going to take a different shape of the fluid element. So now let's take another fluid element that is simply shaped like this. Right? So they say that it's dy in this direction, dz, like we had it there before, and of course dx, if I draw it in 3D, then I would also have a dx. And I'm going to do the same thing. I'm going to consider a force balance on this element. But now the situation is a little bit different. We're going to do this slightly differently. Let's say that I have a reference point will be the center of this element, will be the origin of our system of coordinates. And I'm going to refer any quantity that I need to the value of that property at the center of the element. For example, if I am looking at this side, here's the center. This is the side that measures dy. And I want to evaluate, for example, the pressure here or the pressure here, I am going to do it in reference to the value of the pressure at the center. So let's say, for example, that I call this the pressure on the right, and I call this one the pressure on the left, and the pressure at the center, I just call it P. Then you might recall from math that I can write a Taylor series that allows me to write the value of the function at any point if I know the value of the function at some other point. For example, I can say that the pressure on the right is equal to the pressure at the center plus the distance from the center to the right, which of course is dy over 2, times the first derivative of the function P, the function pressure, with respect to y, because that's the direction that I am moving. And of course, this is evaluated at the center. And the Taylor series has more terms, but fortunately, we don't need to worry about them at this point. We just really need to worry about the first two terms in this Taylor series. So knowing that, if I want to do a force balance in the horizontal direction, then I need the forces in the horizontal direction. So I will have a force on the right, and let's call that the F sub r. And of course, that's the pressure on the right times the area on the right. The area on the right is just dx times dz. So I multiply times dx dz, and I have the force that is acting on the right. And if I want to do the force on the left, then of course that's the pressure on the left times the same area, because the area is the same on those two opposite sides. And so now if I go ahead and use my Taylor series, then I know that this is P times dy over 2 dp dy at the center times dx dz. And then the force on the left is really a similar Taylor series, but now I'm moving to the left, so the dy over 2 is negative, so minus dy over 2 dp dy at the center, same area, dx dz. And since I am doing a horizontal force balance, and those are the only forces that I want to consider, the one on the left and the one on the right, I'm not going to consider, for example, shearing forces that might be acting on the top and bottom, right? So I am neglecting shearing forces. Then those are the only two forces. And if this thing is to obey Newton's second law, then I have that F sub r, which is negative, plus F sub L, that's the sum of forces in the horizontal direction, must be equal to the mass of the element, which is density times its volume, times the acceleration in the horizontal direction, which is the y direction. So that's Newton's second law. So putting everything together, if I do minus F sub r plus F sub L, I am going to be flipping the sign of the expression on the top. All right? So this will be all negative, this will stay positive. So of course when I add, the first term in this Taylor series will cancel out. And the second terms, this will be negative, this will be still negative. They will add together in negative, with a negative sign. So I will have minus the sum of these two terms, so dy over 2 and dy over 2, just give me a dy. dp dy at the center of the element times dx dz. And then on the right-hand side, rho, we can go ahead and write the volume of the element as dx dy dz times a sub y. So if we divide by the volume, obviously the volume appears on both sides, dy dx dz, dy dx dz. Then what we have is that minus dp dy at the center is equal to the acceleration in the y direction. So this is, remember, this is Newton's second law, so these are forces equals MA. Once I divide by the volume, really what I have on the left-hand side is a force per unit volume equal A sub y. So we conclude that the force per unit volume in the y direction is simply negative of the gradient of the pressure in the y direction. Remember, if I now shrink this element to a point, if I take the limit when the element shrinks to a point, dx, dy, dz go to 0, then what I'm talking about is I don't really need to keep track of the gradient at the center because I'm already at the center. So my conclusion is then that minus dp dy is equal to the force per unit volume in the y direction. And if I repeat the analysis in the other two directions, I would of course find that dp dx negative must be equal to the force per unit volume in the x direction, and minus dp dz would be the force per unit volume in the z direction. The force due to pressure, that is, right? So these are all the pressure forces. The pressure forces per unit volume are equal to negative of the gradients of pressure in each of the directions. And that is a very useful result, because if I want to write it as a vector, if I want to write Newton's second law as a vector, that means adding all the three directions, then of course the vector force per unit volume due to pressure, is minus dp dx in the I direction minus dp dy in the j direction and minus dp dz in the k direction. So this vector, which these three components in I, j, and k, is the vector that represents the force due to pressure per unit volume that is acting on a fluid element, but a fluid element that has shrunk to a point. So if you remember from calculus, this can be written simply as negative the gradient operator of the scalar function pressure. So this quantity, negative the gradient of pressure, represents the pressure force per unit volume acting on a fluid element. Okay, so if I put everything together, this is only the pressure side of the story. If I add the weight, then of course remember that the weight only acts in the z direction. So if we add the weight and we put it in the z direction, so adding the weight in z, the weight of course is, as a vector, is negative rho g dv, the volume of the element. But if we do the weight per unit volume, and then this is of course k direction. If we do the weight per unit volume, then it's just minus rho g k. So all we need to do is add in the k direction the value of the weight. So if we have that force added to this, then Newton's second law per unit volume is then minus gradient of P, which represents the pressure forces. Then I have to add minus rho g k for the weight per unit volume. And of course this is equal to MA, but I'm dividing by the volume. So it's just the density times the acceleration. And this equation then is a very important one for us. It's Newton's second law written per unit volume. So it's essentially sum of forces per unit volume equals mass times acceleration, but per unit volume for a fluid. And the one thing that we have to keep in mind is that we neglected the shear forces. Remember, I said that a little earlier. I did not consider any shearing forces. So this result is valid as long as we are neglecting shearing forces. So anyway, so this is then Newton's second law written per unit volume, neglecting shearing forces. But it's a good place for us to start looking at some problems involving hydrostatics. For example, if the fluid is at rest, then of course there is no acceleration. So A is equal to 0. So this equation reduces to the statement that the sum of forces in all directions must be equal to 0. The left-hand side represents the forces. And I can, of course, break it down into the three directions. So if I go ahead and assume that the fluid is at rest and write this down into its components, then it reduces to the following. In the x direction, the component of the gradient is minus dp dx. There is no component of the weight in the x direction, and we said there is no acceleration, so it reduces to this statement that dp dx is 0. The same thing happens in the y direction. And the only direction that has something that is a little bit more interesting is the z direction, because it has the weight. So in the z direction we find minus dp dz minus rho g equals 0. And these are the equations that determine the pressure field under the situation that we have, which is hydrostatics. Is of course telling us that the pressure doesn't change with x and that the pressure doesn't change with y. The pressure only changes with z. And that's why when you have a situation in which the fluid is, this is the free surface, gravity is in this direction. If you are down here within this fluid and you move in any horizontal direction, you don't feel any variation in pressure. So the pressure only changes if you move in the direction of gravity, which is our z direction. So I know that if I draw horizontal lines, all those lines are lines where the pressure is constant. These are constant pressure lines. I only change pressure if I move across those constant pressure lines. So, how do I find that pressure variation then? Well, then we have two options. So our important equation is the last one that we wrote. So is minus dp dz minus rho g equals 0. Or we can write this as dp dz equals minus rho g. So how do we solve this equation? Well, we have to integrate it. If we want to find the pressure field, you integrate this equation. So if you do one integration, that's all you need to do. You get that the pressure is equal to negative the integral of rho g dz. And the limits of the integral will depend on which 2 points you want to use as your limits for your integration. So solving a problem in hydrostatics to determine the pressure boils down to carrying out this integral. Now, how can we solve this integral? It depends on additional assumptions that we make. For most of our problems, in fact, probably all of our problems, we can take gravity to be a constant. The only time you would not take the gravity to be a constant would be if you were solving a problem involving a very large scale of the order of Earth size and so on, that you were, say, trying to make a calculation from the surface to the upper atmosphere. In that situation, you may have to consider a variation in gravity. But for most practical problems in engineering, we can take that gravity to be constant. So the problem reduces to, you can take g constant out, the integral of rho dc. So now, of course, to solve it, it depends on what we say about the density. And obviously, one case is trivial, which is the case when the density is constant, which is what we can do if we're dealing with a liquid. So if the density is a constant, then it can also come out of the integral, and then the pressure is minus rho g. Now, of course, it's just the integral of dz, which is z. And again, it depends on what your limits are. You may have to decide where to put the 0 reference level and where to put the z. For example, if you're doing a problem from the surface of the liquid down, then you may want to put your coordinate system here, starting at the surface. But if I make z pointing in that direction, then of course I'm going in the negative z direction. But then this will just reduce to P equals minus rho g z, where z is measured from the surface down. That's sometimes inconvenient. It might be easier to have a coordinate system that is positive as you go down, so you can define an h that is equal to minus z. And then, of course, then the pressure is simply rho g h. So the pressure varies linearly with depth. So as you go down, the pressure increases linearly with a factor of rho g. And that's what happens, for example, anywhere within water. Another situation that might be a little bit more interesting is if the fluid is not of constant density. For example, let's say that the fluid is compressible, so rho is not a constant. If rho is not a constant, then we have to go back to this step before we pull the rho out. And the only way we can solve the problem is if we know, for example, how the density varies with something else. So one case, for example, is to say, well, let's say that we're dealing with something that can be treated like an ideal gas. Say, for example, we're interested in knowing the pressure variation in the atmosphere. This is air. We can treat the air as an ideal gas. And then if we do that, then we know that we can write for an ideal gas that P is equal to rho RT for the ideal gas law. So if I do that, of course, then I know that the density is P over RT. And then I can go back to this equation and write dP dz is equal to, remember, it was minus rho g, but I'm going to plug this in there, so I'm going to have minus P over RT g. Right? If I have that, then I can separate variables to integrate. So I can write dP over P equals minus G over RT dz. I get that. Now I need to make further assumptions because I can certainly integrate the left-hand side, right? Because I know that this integrates to a natural log. But on the right-hand side, if we make the assumption that G is constant, the gas constant, of course, is a constant, the next question would be, what about the temperature? The temperature could vary with height. If we're dealing with the atmosphere, most likely it will. But as a first approximation, we can say, what happens if it is constant? If T is equal constant, then the integration is again trivial. The left-hand side integrates to the natural log of P. And then the right-hand side, given that G and RT are all constants, just integrates to Z. And of course, there will be a constant of integration that depends on where you put the origin of your coordinates. In this case, it's more convenient to write that constant as the natural log of a constant to simplify the next step. So that means that I can write this as P over C equals, taking the exponential on both sides, equals E to the minus GZ over RT. And then if I specify the value at Z equals 0, again, if I'm looking at a problem where they say this is the surface of the Earth and I'm measuring Z in the vertical direction, then Z equals 0 would correspond to the surface value of the pressure. Let's say that we call that P sub 0. Then, of course, C becomes P sub 0. And the solution is then that P is P sub 0 times E to the minus GZ over RT. So that's another solution. So here is a solution for a problem in which the density varies according to the ideal gas law, but the temperature is assumed to be constant. Compare that to the previous result here, which was the solution when the density is assumed to be constant. So this is for rho equals constant. This is for rho obeying the ideal gas law with constant temperature. So those are two useful cases in which you can obtain a pressure distribution under hydrostatic conditions. There is another one, and let me just, if we take it back one step, so if we go back to this step, right? Remember we had that step a moment ago, before I made the assumption that the temperature was constant. I made the assumption that the temperature was constant, and I arrived at this expression. Skip it here. Right? That was for constant pressure on the top. But if I don't make that assumption, then I might use what is known as the standard atmosphere. And what that is the following. Here is a plot of the temperature versus altitude for what we know as the standard atmosphere. So as you can see, it divides the atmosphere. The lowest portion is the troposphere, then you have the stratosphere, and so on. Let's say, for example, that we're only interested in the troposphere, so the lowest layer, from the ground to about 10 kilometers. Then the standard atmosphere gives you a temperature distribution. So the temperature would be 15 Celsius at ground level, and then it would drop to about, say, minus 55 Celsius or so. At about 10 kilometers. But that gives you a linear distribution of temperature with height. So essentially what that does is, rather than assuming that the temperature is a constant, it gives you the temperature as a function of height. And in the case of the troposphere, as you can see, it's a linear function with a negative slope. The temperature is dropping as you go up. So you can represent it by something like this. You can say that in the troposphere, the temperature will be the surface temperature, T sub A, minus beta Z, where beta is the slope of this straight line. So you can put that in here, into this equation for the temperature, and go ahead and carry out the integration. I will leave that for you to do as an exercise. If you plug that in there and go ahead and carry out the integration, that this is what you get. So you get another expression for the pressure distribution from the ground level, which would be Z equals 0. And that's when P is PA. And then as you go up. So compare that, contrast that to the previous result when we made the assumption that the temperature was constant. Constant temperature is the simplest case. Linear variation of temperature is the more reasonable case for the troposphere. As you can see, if you're doing the calculation in the stratosphere, then the temperature is more or less constant. So you can use this model of a constant temperature for the stratosphere, but you would use this model for the troposphere. Okay, so then I'm going to end it here and come back and talk about manometry and forces in the next lecture.